So in this lab, we're going to use a new simulation software, which is PSIM. Anyone used this simulation software before? Oh yeah. Uh, so I haven't used this before too. This is also new to me. So don't worry, it's not very hard since Ray already gave you the very important two models. So what we should do is only to change some parameter of the model and to build a control loop for motor. So yeah. So first of all, have you all download the PSIM platform already? If no, then start it now. So download the PSIM student version from the canvas, and the serial number is 2630123. So the serial number is in your lab notes. You can find it in the last line of overview. Okay, I'll give you 10 minutes to do that. After 10 minutes, we'll move on. So you can download this PSIM student version from here. When you scroll down at this page, at the module page, when you scroll down to the bottom, you can see this PSIM student version, and you followed by that, you can install the student version. And this PSIM file for Lab 3 is like the model of your Lab 3. So just use this file as your fundamental, and then we will build on our lab from this. All right, so I know this PSIM cannot run on Mac version, but all our lab computer installed on the PSIM. So if you can come to the lab and use the lab computer to run your lab. Okay, then I assume no one have any questions about PSIM installation. Then we will move on to our lab. So the first thing is we're going to modeling the DC motor by its physical model in the PSIM. It's very easy. We already provide the PSIM file for you. So download this PSIM file for Lab 3. And in this file, we got these three PSIM model. And this figure 2 is our first model, which is the model shown in figure 2. So this model is when you open this model in PSIM, what you will say is this thing. And first of all, you will change the DC motor parameters as the parameter provided in your lab note, which is in the figure 3. So do all of this one by one and run the simulation and read the voltage TR and IA and fill the blank in your lab notes. If you have, I'll give you 10 minutes to do this. If you have any question, I will answer you after 10 minutes, okay? And after you finish all this, click run simulation. And code out your VA, and by adding you can add V what you should got is this 3 waveform, and by the time is 95% of PR, so pull out your measurements, find the point that you think is a steady state. For example, here, and find the 95% of this value somewhere you need to calculate, and find out the IA. All right, it's so anyone find what's the voltage value for the speed of 500 rem, 1500 rem. Okay, so now for the volt is 29 volts. For the voltage is 29 volts, I got almost 3000. So what's for the 1500 is 14.5. So change this to 14.5, and now you can get 1.5K speed. And for the TR, what I measured is 141 milliseconds. And what the IA I got is 1.1 M. So any value you get like close from this value is correct. It's like all based on your measurement. Okay, so after this, we will move on to step 2. So step 2, open your file for DC motor figure 4, and let me find my model is so this is the mathematical model for our DC motor. So actually this thing is the same thing with our last model. Just we put this in mathematical way. You can think as this is the transfer function of our physical DC motor. Okay, so in this step, what we are going to find is the value in our transfer function. So how to find the value inside the block is we need to use the menu in our canvas, on our canvas. The menu is, let me see, mode DC motor, so it's this one. So in this node, it gives us the how the value comes from. So let me see. Yes, here. So for the upper is zeros, right? So zeros is this, and the lower is the poles. So the poles is something we corresponding with our inductance and resistance and this inertia and this or this parameter is provided in our first step. So for example, for our first block, this according to this, we are going to find the inductance, right? And in our physical model, our inductance is this one, 0.92. So you know that for A1, it should be 0.92, right? And then according to here, the resistance, you go back here, you find is 2.85. So our A0 is 2.85. And for the zeros, we don't have anything at this at the second order. So for B1 is 0 and B0 is 1. So anyone understand what I'm talking? So I'll show you my first transfer function block looks like this. So in your lab notes, for the TF1 block, the B1 is 0, B0 is 1, A1 is 0.92 million, A0 is 2.85. Okay, understand how this number comes from? And then you need to do your TF2 block by yourself. So TF2 block, you follow this transfer function, okay? So try to find your J and F from your DC motor parameter, and we will come back in 10 minutes. So after 10 minutes, I'll help you to correct your value, okay? Okay, so I will first answer this question is how can you add a new curve into TwoScreen? So when you do the simulation, when you have the result, you first pull out one curve and then you click here so that you add another curve onto your existing one. All right, so let's do this transfer function together. So as I said, for your, according to this two equation, what we know is our B1 is 0. Why I can't change it? B0 is 1, and A1 is our inductance, which is 0.92 million, and A0 is 2.85. And how can we change this value into our transfer function into our mathematical model is so see our coefficiency of B1 and B0 is 0 and 1. The coefficiency for A1 and A0 is 0.92 million and 2.85. So by this, you make this transfer function work. Okay? And so for our second one, which is this one, what we do is we need to find our, let me see, find our inertia and the friction. So the inertia from our model is, you can find from here, 63.5 mil. Yeah, that's right. So you could 63.5 million, and our friction is given here. So it's 5.17. And again, we don't have second order zero, so it is 0, and this is 1. So do the same thing for your second block of transfer function, and you will finish your mathematical model building, and then simulate that, find your TR and 95% of your TR value of IA, fill in these two blank, and compare these two value with your first TR and IA. You will find those two numbers is very close. Okay, so how to find gain block in Psim? Just find it somewhere in here, or you can just copy this gain block and paste it. Y shows two flat line at 0. Two flat line at 0. No, two flat line at 0. I don't understand the question. Should that input voltage? Oh, yes. So here is the input voltage of your your physical model. You need to put this as 14.5. Okay, so by doing the same thing as your first step, you can get your TR and IA, and your IA should similar with your first IA. All right, let's move on to step 3. So open your motor control figure 5 model, and you will find something looks like this. So this part is what we call chopper, also named buck converter. And the first thing is what the input voltage we have is 24 volts, but as we find, we need 14.5 volts to make our motor speed as 1,500, right? So now you don't need to do anything. You first calculate the duty cycle of your buck converter. That's easy, right? So try to find out your duty cycle and your V count. All right, so this duty cycle is easy, right? You just put the input value, you put out divided on input. So what's the value you want to use is we want to use it 14.5 divided on the input voltage is 24. So what we got is 60.42. Where's my percent? And our VCOM is maximum voltage here. Here our maximum voltage is 10 volts. So it's 10 volts times our 60.42. 0.42, which is 6.0 volts, right? So change your VCOM value, and now when you change the value of this VCOM, you put a voltage measurement here, which means you measure the output of your chopper, your output of your buck converter. So try to find the value of this measurement and put the value in here. Alright, did you all got the value? I got the value as around 16.8 volts. So you might have questioned that we designed our buck converter, and by the calculation, it should give us 14.5 volts. But actually what we are measured is 16.8 volts, right? Because this PWM generator, it uses like a 6.04 volts with a triangle wave, and to cut the triangle wave. So the PWM waveform is not exactly a triangle, not exactly a square wave. It has slope. I'll show you the waveform. So can you see that this is not square wave? It gives you a slope, and the measurement, and the how to say, the output use the value from here to here. The on state use the value from here to here. So it will be slightly larger than what we designed, but it's okay. So just use this value, use this 16.8. I hope everyone got the same value with me. I got the 16.8. And now you need to pull out your IA value. And zoom in that. And pull out your cursor. Find your maximum and minimum value of your IA. See, my maximum value is 1.16 and minimum is 1.00. So now you know the delta value is 1.54, because I put it like vice versa. So the delta value is 0.154, right? So the average value of IA, we just use the average of these two numbers, make it easy. And then you need first put the maximum value here, minimum value here, and average value here. I'll put mine. I guess so the delta IA. I'll put my one. You need to measure yourself. Don't use the same value with me. And now we need to calculate the torque ripple in percentage. Because the torque ripple is correlate with current ripple. So actually we're doing the current ripple in percentage. So here what we do is use our delta IA value divided on average value IA average, which is and we find is my one is 14.7. So you calculate your one and let me know what your value is, okay? All right, so yeah, good. I can see all of you got the percentage is 14 point something, so it's larger than 14%. But in our lab notes, let me see. The requirement is we want the torque ripple less than 5%. So apparently our converter doesn't match this requirement. So we need to add an inductor to lower the ripple. So now we open this document and it's we use this equation to calculate our inductance value. So, yeah. So here, our delta I max is we using. Let me pull out. So look at this equation, okay? So what we have is for the left-hand side, we want to know our delta I max. Our delta I max, now we want it's 5% of our average. So the left-hand side is 5% times your average IA value. And our right-hand side, the upper is E, the E is our input voltage, so it's 24 volts times TH is our frequency period. So, oh, sorry, it's 0. What? It's 5% in your question. I don't know what your question is. Okay, so let's move on. 24 times TH is your period of your frequency. So it's 1 over 40,000 kilohertz. And the low is 4 times inductance. So solve this equation and you will get your inductance. My inductance is 2.76 milli. So don't use the same value as me. I know you have different average value with me, so you can't be the same value as mine. So calculate your own value and All right, anyone got the value of your inductor? Okay, I can see 2.77 milliamp. Yeah, that's right. So any value close to that is right. Good. Okay, then what you need to do is put inductor here to smooth your output of buck converter. Okay, so put inductor here and change the value to the value you calculate. Okay, so then by the end of part one, what you need got is this physical model and your mathematical model and your full mathematical model. So this is all what we need to get from part one. We haven't add any control onto our model. We just build up our model. So for step two is we are going to start to add on the control loop onto our model. So we have two control loop. One is current control and the second one is speed control. So for this part, we start with our mathematical model. You first have to read your lab notes. The whole page of your page 6 to page 7, the whole thing, and you need to use the lab menu of this one to find the equation to calculate your tau E and tau L. And you need to fill in these two blank and to finish the the control loop. Okay, so what I think we can do is you do part 2 yourself, and this lab is for 2 sessions. So for the next session at the very beginning, we will do the part 2 together. And for the part 3 is all by yourself. I will not give you any instruction for part 3. So we will do part 2 together at the very beginning of next session. So try to do part 2 yourself first. And I will only quickly help you to understand what happened in part 2 next week. You only need to upload one report for lab 3. So after we finish lab 3, you then to write the lab report. Okay, so this is all about today's lab. We finished the part 1, and for the week after mid-break, we will do part 2 together. So after next week's lab, I'll help you finish part 1 and part 2, but part 3 is all by yourself. I will not give any instruction about part 3. So yes, I guess that's all about today's lab. I will edit this recording and upload this recording onto Canvas later. So you can watch this recording and do your lab at home. That's it. See you the week after our mid break. Okay.